Hi everyone, it's Mr. Zarzak, and I am going to show you how we apply right-hand rule, specifically right-hand rule number 1 in this video. Okay, right-hand rule number 1 says, imagine that you have a wire, okay, and some current flowing through it. You use your thumb, okay, and then you take and you curl your fingers around the wire, and that tells you the direction of the magnetic field. So if we can imagine that this wire has a current flowing upwards, okay, I would point my thumb along that direction. I would just curl my fingers around like that. Okay, and so what happens is this actually makes a circular magnetic field. It gets weaker with distance from the wire, but it makes these circles. So there's a definite direction in which the magnetic field moves around the wire, which is kind of crazy, but also kind of cool. All right, so if my finger is pointing, or if my thumb is pointing up here, okay, we have to imagine, like, if you can kind of picture like the plane, like this plane that's kind of along the same direction of your screen. Okay, well, if I curl my fingers around, the direction of my fingers right when it breaks the plane is just the direction that's tangent to this circle. So you have to imagine this circle going around the wire. My fingers would actually be pointing out of the page towards you right when we would reach this plane that is along the same dimension as like your screen right now, or if you're looking at a picture like at the page itself. Now, when I come around here, if I was looking at a plane that was more like this, when I curl my fingers, okay, well that curl, the direction of my fingers pointing is actually this way, okay? So if this is the direction of my plane, well then at this point, this is the direction of my magnetic field. Okay, if I keep going around like this, I'm curling my fingers around, so right when I get back to that original plane that I started with, right when I break that plane on this side of the wire, the direction of the magnetic field is in towards me. And if I take it even one step further, you can see my fingers peeking back through here. If I come all the way around, okay, when I'm behind the wire, the magnetic field is actually pointing in this direction, okay? If I reverse the direction of the current, okay, well then all that flips, all right? When I break the plane on this side, now if the current's flowing downwards, the magnetic field is coming out of the screen towards you. Whereas if I go in a plane that's oriented like this, okay, when my fingers break the plane, the magnetic field is going this way. If I continue around on this side of the wire, my fingers are actually pointed into the screen at this point, so that would be the direction of the magnetic field would be into the screen. Okay, and then all the way back here, I'd have to curl around again. I think it's probably easier for me to go this way. Okay, if I put my thumb like this, hopefully you can see my fingers pointing along this direction relative to plane like this, okay? Now, let's take a look at this from above. All right, so here's that same wire. Imagine it coming towards you. All right, so from your perspective, we'd say that the wire would be coming out of the page. Okay, or we're looking at this wire from above, looking down on it with the current flowing up towards you. Okay, so again, here's my thumb showing the direction of the current. So if I take and I curl my hand around, okay, see what I'm talking about here? So now we're curling around, we're making a circle that's rotating along this direction. Okay, this is the direction of the magnetic field. So from our perspective up there, all right, we see that the direction of rotation is counterclockwise. Okay, and if I bring my hand around at this spot here, okay, well then the direction of the magnetic field is this way, the direction of the magnetic field is this way, the direction of the magnetic field is this way, the direction of the magnetic field is this way. It's always tangent, okay, to the curve. All right, now again, if I reverse the direction of the current flow, if the current is flowing downwards, all right, so from your perspective, so the wire, the current of the wire is now coming out of the screen. Okay, well then if I curl around here, you can see again, here's the direction of the magnetic field. It's making a loop around the wire that's now clockwise. Okay, see the difference? So like here, it would be in this direction, this direction. If I curled around here, my fingers here, let's see if I can scooch around this way. So then this direction was just following the direction, okay, of that curve around. All right, and that's right-hand rule number 1. All right, so the magnetic field around just a straight wire isn't all that useful. All right, so to make it even more useful, what we do is we end up bending that wire into a loop. Okay, so imagine like here's my wire, maybe my positive terminals over here. Current's gonna come and follow through this loop, and then move on to the negative terminal over here. Okay, so applying that right-hand rule number 1. Okay, so here comes my current. You can see if I curl my fingers around using my right hand, all right, right when I break the plane out towards you, then down, back into the screen towards me, okay, and then up here back behind the wire. Okay, so nothing new there. It's when we get into the loop, okay, that this starts to get interesting. All right, so if I trace this out with my hand, all right, look, the current, we're looking at the current, taking a snapshot of it right when it's in the loop. All right, notice how my fingers, if I curl them around, right when they're hitting this plane of the loop, which is the same plane as your screen right now, okay, my fingers are like coming out of the screen. So we say that the magnetic field here is out of the screen. All right, well, if I rotate along the wire, say up to here, we'll notice that my fingers are still pointing right into the plane of the loop, okay? And I can trace this all the way around. My fingers always point into the plane of the loop. Now I might need to reorientate my hand here in order to make this work, but my fingers always point into the plane of the loop for the entirety of the current flowing through the loop all the way until I get over here. Now once I leave, okay, it's just back to a long straight wire. We don't care about that. I'm talking about inside the loop. All right, now why does that matter? Well, the direction of the magnetic field, okay, like you gotta remember the current's going around the entire loop, so there's current that's creating magnetic field in the loop over here and over here and over here, all simultaneously, all right, but the direction of the magnetic field is always into the plane of the loop, all right? Now, if I reverse my direction of current flow, like if the current was flowing this way, all right, well, the direction here, look at this. Now, as I move around, now my fingers, if I curl them around my looped wire, okay, are always just back in towards me. They're still breaking the plane of the loop, okay, pointing the same direction as I move around. My fingers are always pointing into the loop, okay, or into the plane of the loop, I should say, as I go around. So if I just change the direction of the current, well, all that happens is the magnetic field inside here is into the screen as opposed to out of the screen. See that? All right, all the same direction. That's uniform, okay? That's the first part. All right, let's go back to the current flowing this way, so just because it's easier for me to get my hand over here, all right? Let's say I took a snapshot of the current right when it was at this lowest point, it'd be like 6 o'clock on a clock face or something, okay? So right at the low point. All right, well, the magnetic field that's generated by the current in the wire right here is going to be the closest, the closer I am to the wire. So in other words, like right here, this is where the magnetic field is the strongest, and as you get farther away, the magnetic field gets weaker. Okay, so again, like the source of the magnetic field is the current flowing in the wire, and that magnetic field gets weaker with distance. So as I move from here up to here, the magnetic field, it points the same direction, but it gets like weaker, 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 weaker. All right, well now, we have to remember though that there is another current flowing through the wire. I mean, it's the same current, but there's another chunk of the current that's flowing through the wire up here, okay? That's also generating magnetic field that is the strongest to the wire at this point. So like the little segment of current that's up here generates a strong magnetic field here that gets weaker, 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 weaker. All right, so you have two things that are producing strong magnetic fields that get weaker, 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 weaker. Well, the funny thing is here you have a strong contribution from this part of the loop and a weak contribution from this part of the loop. All right, here you've got kind of like a middle-sized contribution from the magnetic field from this part of the loop and a middle-sized contribution of the magnetic field from this side of the loop, all right? What's crazy and what's awesome, okay, is that the magnitude, when you sum up these components, it's constant for everywhere in the loop, all right? And so why we like to use these loops is it gives us a location where we can generate a uniform magnetic field, both in terms of strength and direction, as long as we stay inside the loop. And how do we control that? By cranking up the current. The strength of the magnetic field inside this circular plane is proportional to the current in the wire. Now, there's some magnetic field out here too, okay, but we typically don't worry about that for a couple of reasons, okay? One, it's not uniform. So like here, the magnetic field is pointing, towards me. All right, great. So what? Well, if I look up here, like there's another contribution. Okay, if I do this, let's see if I twist my hand around, there'd actually be a contribution from the current up here that's actually pointing the other direction. Okay, so they're not exactly equal because the distances aren't equal. But the point is that you have opposing magnetic fields out here that are non-uniform in direction. This outside, the magnetic field becomes weak and unreliable and it trails off really quickly. It means it's just not very useful to us. What is useful to us is inside of here. All right, if the current is flowing in this direction through the loop, okay, well then we get this uniform magnetic field this way of the same strength everywhere inside this loop of some radius, just radius r, versus if the current is flowing this way through the loop, okay, well, the magnetic field is flowing this way. So imagine what we're doing here is we're creating an electromagnet where you can reverse the polarity of the magnet just by reversing the direction of the current flow. All right, now I don't know how obvious this is on the camera, but in order to make this little demo, you can see there's actually two parts here where there's like double loop on the bottom, okay? And this is just a demo, all right? But you have to imagine down here, okay, that, well, we're getting current flowing through the wire in the back part of this loop that's generating a little bit of magnetic field. Okay, and then when we come around again, on the second turn around, we're also getting a secondary contribution from here. And this is only happening where the overlap is. So if I was really making a loop of wire, I wouldn't have this overlap unless I wanted to do so intentionally. But imagine if you could just wrap more and more loops round and around and around and around, like kind of like you were like winding up like a donut kind of a shape. Well, every time you made a loop, okay, we'd have another segment of current. So like down here, I got two segments of current that are going to flow the same direction. Those add to the magnetic field, okay? And because these are factors, these just add up. These components, they add up. So what we can do is we can twist around more and more loops, and every time we twist around a loop, we get a multiplier to the magnetic field strength for the same current. Okay, now if that's not engineering, I don't know what is. All right, so if I can take a loop of wire and create a uniform magnetic field inside of it, well then I can boost that by putting more and more loops on top of one another. The problem is eventually all those loops, okay, start to stack up on one another, and the geometry of this thing changes. When the length of this cylinder, okay, starts to become a factor, when it becomes about 10 times as long as the radius, okay, we stop calling it a stack of loops or a toroid, and we start calling it a solenoid. So this is just a solenoid. We'll get into the equations and the math later, but you might have played around with these before. This is an electromagnet. Okay, I've got a metal lead here that connects to the wire, and this loops round and round and round and round and round, and then the other side, here's the other metal lead. Okay, so if I take this and I connect this to some wires, okay, to my power supply, okay, if I turn on the electricity, okay, I will have an electromagnet. Now, to get this to work, I got some paper clips here on the table. I actually have to crank up the current pretty high. It's actually off the chart here just to get a very small amount. You can see that it's struggling, but it's kind of picking up the paper clips. If I turn the current down, okay, they fall right out. All right. So how can I make this better? All right. Well, I could get a thinner wire, okay, and so that I could squeeze more turns into the same space. That gives me a stronger electromagnet proportionally. I have to be careful though, because current in the wire heats things up. So if I put too much current through the wires, then they melt. Okay, so there's like a trade-off with this. Something else that we can do with this is kind of neat, is if inside, okay, this is just hollow right now. Say, oh, hello. Okay, so right now we have a magnetic permittivity of air, which is essentially that of a vacuum. It's another constant that we've measured. Okay, well, much like with electrostatic forces, we can put a dielectric to change the physical properties of the space inside. We can do the same thing with magnets, but the key is that it has to be something that is ferromagnetic. So this is steel. Okay, so like you can see, I've got a permanent magnet here. So like this is something kind of like the paper clip that responds to magnetism. All right, and steel has iron in it, which makes it one of the best materials to put inside of a solenoid. So anyway, so going back to this again, I have to crank up the current really high to get any appreciable electromagnetism. As soon as I turn it down, okay, well then it gets weaker. Well now look what happens when I take and inside the solenoid, okay, I put this metal core, okay, this iron core. Now if I turn this up, okay, so that's about where the current was before. Okay, man, now look how much stronger this is now. Now I can pick up, I don't have to get on top of them or anything. And what's neat is if I take and I move the iron core through the inside of the solenoid, okay, I maintain that magnetism until I remove the iron core, and then you can see the iron core itself is not magnetic at all. All right. One more thing I wanted you to see with this. Okay, so if I just put the solenoid down like that, I've got this permanent magnet over here. Okay, so this is a neodymium magnet. It's a pretty strong magnet. Okay, you can see it can pick up paper clips and stuff. But anyway, so if I'm just going to put it along the edge here. Okay, now this is just for fun. So watch the little electromagnet. Turn on the current, and oh, it spits it right out. Okay. Now I'm going to take the same magnet. I'm going to orient the same way along the edge here. I've got it marked so I know which side of the magnet is which. Okay, and I'm going to take. I'm just going to reverse the wires going to the power supply, so I can reverse the direction of the current flow. Now when I turn it on, instead of spitting the magnet out, it sucks it in. Okay, why? Well, because I've reversed the polarity of the electromagnet. In other words, I changed the direction of the magnetic field. All right. We'd have to figure out from right-hand rule. Let's see, actually we can do it. So here, let's see, we're going in this way, so the current's flowing this way. So here, the magnetic field was flowing into the solenoid. When I had the wires reversed, the current was flowing the opposite direction. It was flowing out of the solenoid. Okay, so I just got lucky with the direction of the permanent magnet for that it went. Well, I guess the North Pole must have been on this side. Pretty neat though, huh? All right, thanks for watching.